When injection pressure suddenly collapses mid-stroke, molten metal freezes before it can fill the cavity. The result is an immediate catastrophic cold shut. This module addresses the engineering mechanics of high-pressure die casting hydraulics, specifically the management of accumulator energy. On the shop floor, engineers are constantly adjusting the machine interface. To optimize casting quality, they frequently tweak the fast short speed and the fast short length. However, these daily kinetic adjustments often expose a widespread operational error. Out of habit, operators will leave the accumulator charging pressure completely untouched. This forces us to ask a strict engineering question: is a fixed accumulator pressure ever correct when other parameters shift? The answer depends entirely on whether the accumulator holds enough hydraulic oil energy to support the new speed and length demands. When operators ignore the mathematical relationship between kinetic adjustments and hydraulic supply, they inadvertently engineer their own casting defects. This data table establishes the baseline. Before making any interface adjustments, we calculate the machine's absolute limits using fixed constants, dividing the short force by the working pressure to find the exact injection cylinder area. With that area defined, we know the accumulator must deliver high pressure oil to satisfy two entirely distinct physical demands simultaneously. Looking at the left side of this diagram, the first demand is oil flow. Measured in liters per second, flow creates the fast short speed. The second demand is oil volume. This dictates how much actual fluid is required to complete the fast short length. Because both speed and length rely on the fixed cylinder area, any interface adjustment to either parameter directly and permanently alters the accumulator's energy demand. We can calculate exactly what happens when an engineer decides to simply dial up the short speed. This chart maps oil flow against velocity. Increasing the speed by a mere 0.5 meters per second does not scale linearly. It triggers a disproportionate demand on the system's flow capabilities. Specifically, moving from 2.0 to 2.5 meters per second forces a 25% spike in oil flow demand. Adjusting the short length creates a different problem. Extending the length directly cannibalizes the machine's finite oil reserves. This diagram compares cylinder volume demands. Increasing the short length from 250 millimeters to 350 millimeters forces the accumulator to supply an exact non-negotiable volume of extra oil. Failing to supply those 3.37 liters ensures the plunger speed will physically drop as it nears the end of the filling cycle. The fixed pressure habit treats these massive physical requirements as invisible. The machine interface accepts the new settings, but the physics dictate failure. Consider a stress test scenario where an engineer increases the short length to fill a larger part but stubbornly leaves the accumulator pressure fixed at the standard 140 bar. This diagnostic scenario models case C. We compare the calculated volumetric demand of 11.81 liters against the 9.49 liters of actual oil available in the accumulator. The math reveals a critical shortage. The machine is missing 2.32 liters of oil required to finish the stroke. In reality, the accumulator drains entirely dry before the shot is complete. The heavy hydraulic piston stutters and end filling speed violently drops. This lack of terminal velocity allows the metal to cool rapidly, creating cooled shuts, gas porosity, and visible flow marks on the final part. When the math fails, the casting fails. The habit of leaving pressure fixed is mathematically responsible for this end stage quality collapse. To recover from this exact 2-liter shortage, we have to elevate the accumulator's charging pressure. This cross-section compares internal capacity. By compressing the nitrogen gas further with a modest 10 bar increase in charging pressure, we physically expand the usable oil capacity inside the shell from 9.49 to 12.52 liters. Applying this capacity to our failing scenario, case D shows the result. The 11.81 liter demand is now fully supported and a safe operating margin is restored. But higher pressure introduces severe mechanical risks. Pushing oil at 150 bar drastically increases the kinetic energy at the end of the stroke, elevating the danger of flash, die wash, and hydraulic shock. Elevating pressure solves the volume shortage, but it introduces shear force risks. Therefore, pressure must be a precisely calculated choice, never a default setting. By combining flow and volume mathematics, engineers can map out the exact boundaries of their machine before a single shot is fired. This matrix synthesizes those variables. It provides clear diagnostic outcomes for different speed, length, and pressure settings, showing exactly where a setup moves from stable to risky. However, this math also challenges the assumption that you can solve every quality problem by simply dialing up the pressure. KC illustrates an absolute system limit. With highly aggressive settings, the demand hits 13.50 liters. Even at the maximum safe pressure of 150 bar, the accumulator can only supply 12.52 liters. The math is impossible. Pushing past this boundary requires physical hardware upgrades like larger accumulator tanks or higher capacity proportional valves, not just screen adjustments. Mathematics reveals the hard boundary between an easily solvable parameter issue and a fundamental hardware bottleneck. This decision logic flowchart governs every pressure adjustment on the floor. It dictates when to hold, when to verify, and when to restrict pressure changes. This validation checklist details the required next step. Before adjusting pressure, engineers must interrogate the machine's actual shot profile data, searching for specific evidence of speed decay or pressure collapse. The rule shown here is definitive. The assumption of a fixed accumulator pressure must be abandoned. Instead, apply a three-step sequence. Calculate the die demand for flow and volume. Check the short profile evidence. Only then decide on the required pressure. Accumulator pressure is never guesswork. It is the calculated mathematical heartbeat of defect-free die casting.